Through this video, I am going to explain the second part of the theorem, that is the converse part of the theorem. A graph is bipartite if and only if it contains no odd cycles. Okay, so in the previous video we assumed the first part, that is a graph is bipartite, and we proved the second part, that is it contains no odd cycles. So here in the converse part, what we are going to do is we are going to assume the second part and we will prove the first part, that is we are going to assume G contains no odd cycles. So here in the next line, that is the cycle of G is of even length. If there is no odd cycle, means what does it mean? It means that the cycle of G is of even length, right? So that is what we have assumed here. So here, without loss of generality, you are assuming one more thing, that is we are assuming G is connected, that is the graph G is connected. Okay, so here we are going to prove that G is bipartite. So to prove this, what we are doing is, first you are considering an arbitrary vertex of graph G. That means any one of the vertex from the graph G. Okay, so using that you are defining two things, that is, let x equal to, you are considering a set x. So you are saying that this x is a set of all x belongs to V such that d of u comma x is even. What is mean by this? What is mean by this? It means that if you find the distance between this arbitrary vertex u and any other vertex x, if the distance between these two is even, then this arbitrary vertex u is in the set x, and also you are saying let y is equal to set of all y belongs to V such that if the distance between this arbitrary vertex u and any other vertex y is odd, then this arbitrary vertex u is in the set y. Okay, this is how you are assuming. Okay, this is let condition, right? It means you are assuming. Now clearly, so from this what you can say, clearly x intersection y is equal to empty. It means if you find the x intersection y value, you will get empty, because here in the x set you have even vertices and in the y set you have odd vertices. So when you find the intersection of this x and y, there you could not find the common vertices, right? So that is why clearly x intersection y is equal to empty, and when you find x union y, you will get whole vertex V. That it means in the set x you will have some collection of vertices, in the set y you will have another set of vertices. So if you find the union of these two x and y, what you will get? You will get all the vertices, right? So that is why you have written here that x union y is equal to capital V. So here what you are going to prove? You are going to prove this x, y is a bipartition of G. If you prove this, then you can say that the given graph is bipartite. If there is bipartition, then you can say that the graph is bipartite graph. So that is what you are going to say now to prove x comma y is a bipartition of G. Okay. And now what you are going to do is you have to draw this figure. Okay, from this figure you are going to write something. Okay, from this figure you will write all these things. Okay, so you have to be clear with this figure. So have a look at this figure. So here this is the vertex u, here is the vertex u, and here is the vertex v, and here is the vertex w. Okay, and the distance between this u and v is, you are denoting the distance between u, v as p, and the distance between distance from u to w as q. Okay, so here you have another vertex u1. Okay. Okay, so I hope you understand what I have drawn in this figure. So here let's see what is there in the proof using this figure. Okay, so suppose the first line, suppose v and w are two vertices of x. You are taking two vertices and you are saying these two vertices are from the set x. Okay, so also let P be the shortest UV path of length m. Okay, so here what they are saying, P be the shortest UV path. That is, this UV path is denoted by P, and this is the shortest UV path, and they are saying that P is the, and this shortest UV path is denoted by this P. Okay, and they are saying the length of this UV path is m. Similarly, let Q be the shortest UW path. Okay, UW path from U to W. If you want to go, then what you will do? You will start from here and you will reach U1, and after reaching U1 you go to W, right? So they are saying let Q be the shortest UW path of length n. Okay, they are denoting this UW path as Q, and then let U1 be the common vertex to both P and Q. You know that, right? From the figure you can say this U1 is the common vertex. Even for the UV path you have to go U1, only after reaching U1 you will go to V. Also for UW path you will start from U, you reach to U1, after reaching U1 only you can go to W. Right, so that is why this sentence, let U1 be the common vertex to both P and Q. Here U1 section of P and U1 section of Q has same length, right? So here if you want to go, if there is a UV path that you have denoted it as P, so if you want to if you talk about UV path, then how will you go? You will go U1, and after reaching this you will go to V, right? So okay, if you want to go UW, if you talk about UW path, what you will do? You will cross U1, after that you go to W. So here from this to from this P and Q, what you can say, this U1 section of P and U1 section of Q have same length, right? This is same length, so you are denoting it as I. And then let P1 be the U1V section of P, and you are assuming some other thing. These all, everything is let. It means you are considering to prove the theorem at the end. Okay, so here let P1 be the U1V section of P. So this is denoted by P1 now, right? In earlier step what we have done, you are denoting U1V path as P and UV path as P and UW path as Q, and now what you are doing is you are denoting this U1V path, U1U section of P as P1 and U1W section of Q as Q1. Okay, and they are also, we are saying that they are also, that is the length of this and the length of this also equal. That is what you are saying, they are also have equal length. And then consider P1 inverse Q1 is the VW path. It means, what is meant by VW path? You are starting from here, right? VW path means V, and from V you will go to U1, and then from U1 to you go to W. So here what you are working in reverse, right? So that is why here you have denoted as P1. Already in the previous step we have wrote U1V is P1, right? So here in this line you are, what you are doing, you are talking about V u1, v u1. It means you are working in the reverse. So P1, here you are writing P1 as P1 inverse. I hope you understood that why you are writing inverse here, because you are working in a reverse manner. So from V to U1 you are going. So that is why the P1 is denoted as P1 inverse here. So consider P1 inverse Q1. Okay, right? So VW path means what? This is P1 inverse and this is Q1, right? So that is what P1 inverse Q1 is the VW path. The length of this path is even. Am I right? How you are saying that this is even? Because from V to U1 the length is 1, and from U1 to W the length is 1. So 1 plus 1 is 2. So that is even. So that is why we are saying consider P1 inverse Q1 is the VW path. The length of this path is even. Now if we join V and W. So if we join this V and W, if you put a line like this, if we join like this, then what will happen? Using an edge, if we join V and W using an edge, then we get a cycle. It formed a cycle, right? What cycle? P1 inverse Q1 UW. This is the cycle. This cycle will be formed and the length of this cycle is odd, right? So which is contradiction to G contains no odd cycles. In our assumption, what we have wrote? G contains no odd cycles, but here we got the cycle is of odd length. So here you are getting a contradiction. 2G contains no odd cycles. So our assumption V and W are two vertices of X are wrong. So V and W are the vertices of X is wrong. Okay, this assumption is wrong. Okay, this assumption is wrong. So what you are saying? In the final, no two vertices in X are adjacent. So in a bipartite graph, if there are vertices, this is the sum of the vertices in the set X, and here you can see sum of the vertices in the set Y. So here what they are saying, no two vertices in X are adjacent. It means there you could not see any vertices in this manner. Okay, in this manner. In X also you could not see the adjacent, no two vertices in X or adjacent vertices. In Y set also you could not see any adjacent vertices. Okay, how the vertices will be? Only if you consider this edge, one end of the vertices will be in the set X and another end of the edge will be in the set Y. You can consider any sets from the bipartite graph, it will be like that. Okay, one end of the edge will be in the set X and another end will be in the set Y. So here what is our conclusion? No two vertices in X are adjacent and no two vertices in Y are adjacent. Hence, if it is like that, then what you can say, that graph is bipartite graph. So hence the proof.